Kovalevsky and partial differential equations. Born Sophia Valentyevna Korvan-Krukovskaya, but she preferred Sophia Kowalevsky. She was born the 15th of January, 1850. Her father was the Lieutenant General Vasily Valyevsky Korvan-Krukovsky of the Imperial Russian Army, and her mother was Elizaveta Schubert of the German Schubert family. She grew up in Russia on her father's estate, and he encouraged her pursuits in math. Because he was a lieutenant general, he procured basically the best for her. Her two tutors growing up were Malevich and Strena Lubinsky. One was Polish, one was Russian. About 12 or 13 years old, nihilism started taking over Russia, and she was introduced to it by her sister. So nihilism played a huge part in her worldview and how she operated as she got older. In addition, it also influenced how she managed to go ahead going forward in her education, because at this point, unmarried women could not travel by themselves. This is where Vladimir Kovalevsky, hence the last name, comes in. Nihilism, one of the tenets of nihilism was false marriage, in which you married somebody and then promptly left them to go do whatever. And Sophie did just that. She married him, left him, and went off to go do her own thing. Her ultimate goal was to gain her doctorate, get a position of teaching at a university, and she did that. She managed to do all of that. However, on her way to accept it, in the 10th of February, 1891, she died of pneumonia. As mentioned, she was home tutored for her primary education with a focus in mathematics. She left Russia in 1867, about 2 or 3 years after she got married, so she was about 17 at the time, to begin her more formal education. Her first stop was the University of Heidelberg, and here, this is where you'll see that her being a female really made things hard for her. She had to go to each of her teachers and get their permission for her to be in their class. The person that gave her the most trouble ended up being the person who invented the Bunsen burner, so let's just think about that for a second. But she did end up attending, and she managed to get all the way through Heidelberg, and then she ended up going to the University of Berlin. University of Berlin outright said, no, you can't come here. Instead, she ended up meeting with Karl Weierstrass, one of the teachers that worked there. And if you're in numerical analysis or real analysis, you know that person. He originally did not believe in her. He didn't think she could do it. But he gave her a set of 3 problems, and those 3 papers, he looked at it and he's like, yep, okay, yeah, we're going to go ahead and get this application done for you to go ahead and get your doctorate. The first work she did was on Laplace's stuff, so Saturn's rings. The mathematician Laplace did previous work on a problem and came to the conclusion that certain cross-sections of the rings were elliptical. Kovalevsky, however, proved that this wasn't the case and that they are in fact egg-shaped ovals that had symmetry about a single axis. The second one was abelian integrals. Abelian integrals focus on complex equations and the integral therein. However, he died before he could finish that work, so Weierstrass handed that problem over to his students, including Kovalevsky, to generalize. Kovalevsky demonstrated the possibility of expressing specific types of abelian integrals with elliptical ones. And the last one, which we're going to get to in a second, is called the Cauchy-Kovalevsky theorem, and it focuses specifically on partial differential equations. They submitted these 3 papers and said, hey, we think this is good enough for her to get her doctorate, and they agreed. But because she technically wasn't a member of the university and she didn't have to take the tests or the classes or any of that, it was granted in absentia in 1874. So she was about 24 when she got her doctorate. Going to the Cauchy partial differential equations, yes, it looks like Greek, and I'm sorry. The easiest way to explain what's happening is the top one is the Cauchy specific partial differential equation, and the second one is taken with the derivative with respect to time. It was Kovalevsky's job to simplify it, which she did with this. I know this doesn't make a lot of sense, and it's actually really hard for me to explain, but it essentially says that for a partial differential equation involving a time derivative of order n, the solution is uniquely determined if the time derivatives up to order n minus 1 of the dependent variable are specified at a single surface, provided the surface is a free surface. To give you some background on what that means, a free surface exists on a boundary between two homogeneous fluids, the surface of a fluid that is subject to zero parallel shear stress. Basically, if the surface doesn't have a lot of friction on it, this will work. So why is this important? First and foremost, because it generalized Cauchy's theorem so well, it has become part of the foundation for partial differential equations. It also proved the local existence and uniqueness theorems of analytical partial differential equations. And what I found the most interesting is that it is valid for analytical functions that are both real and complex, which is hard to do, so that's kind of really cool. The other thing that I forgot to put on here is a guy named Louis. I couldn't find a year for this, but he went on to show that it doesn't work for all smooth surfaces. It still holds for complex and real, but it doesn't hold for all smooth surfaces. But a guy by the name of Masaki Kashiwara went back and proved that it does work for systems of linear partial differential equations, and that was back in 1983. So Sophie went from having a really bad life because she got married, got divorced, got back with him, got divorced. She almost didn't get her teaching position, and then she got her teaching position and then died on her way to get it. But because her work is so enduring, it kind of makes up for it. So does anyone have any questions? Awesome.